Okay. So, so in tomorrow's lecture, Jeff will explain how to use all the results we obtained so far with the spectrum of percolation to deduce that when you consider thermal fluctuation in percolation and you define this model of dynamical percolation for which you've seen a movie the first day, you have exceptional times where infinite clusters suddenly appear. So somehow the last lecture will be very different from all the others. It will just take as an input the results on the spectrum, but won't prove anything on the spectrum, and explain to you how to use these to extract exceptional times. So today, so let me start by recalling what we know on the spectrum of percolation after the previous lectures. So if we look at this energy spectrum that we considered many times already, which is the contributions of the Fourier coefficients of size k, so if we plug this as a function of k, we get some shape. And in the third lecture and the fourth lecture, we've seen that hypercontractivity, which was useful to understand the influences of Boolean functions and so on, hypercontractivity in the case of percolation enabled us to show that the spectral mass diverges at least at this speed. So this was hypercontractivity. Then, 2 lectures ago, Jeff explained that using randomized algorithm, so a completely different idea, using randomized algorithm, you can actually push the spectrum further away, and you can go on the triangular lattice all the way to 1 to the 1/8, n to the 1/8. So we have a polynomial lower bound on how fast the spectral mass diverges. And 2 days ago, Jeff showed that there is a positive fraction of the spectral mass. So if your Boolean function are, say, into -1, 1, -1 if there is no left-to-right crossing, 1 if there is a left-to-right crossing, by Parseval, you know that all the spectral mass which is here sums to 1. So saying that a positive fraction of the mass lies here says something like maybe 1/2 of the spectral mass has size of order n to the 3/4. So in fact, it's not exactly n to the 3/4. There are little corrections here. So the real behavior is the number of points in a square times the 4-arm, the probability of having 4 arms. And Jeff explained that this quantity is the expected size of this spectral sample. So I'll recall what this is. This was this random subset of the bits which correspond to our spectral measure. So last time, Jeff explained that at least half of the frequencies, somehow, they are of this size. And we know that most of the frequencies, they are above this threshold. So now the purpose of today is to show that everything lies in this regime here. So somehow we'd like to prove a kind of 0-1 law that with probability 1, a spectrum is this big. So let me just translate what this picture means in terms of the percolation picture. So if you take a window of size n, say a square, but it could be a rectangle or anything. Now sample a critical configuration omega in this. So in this picture, you see a lot of clusters. From Vincent's course, you know that you see a bunch of SLE6, a lot of rich geometry here. Now, let's shuffle a little bit the randomness here. Let's noise it a little bit. And let's apply noise epsilon of n much larger than this. Maybe not much more, but just this tiny noise, like that. And let's go from this configuration omega to the noised configuration omega epsilon of n. So in this picture, a tiny fraction of the bits are resampled, maybe these ones. And what this statement tells you, the fact that a positive fraction of the spectral mass lies here, it tells you that there is some decorrelation between the left and the right. It tells you that you lose some of the information. And this is not so hard to believe because between these big clusters, well, you have many pivotal points, and the amount of these pivotal points is about n to the 3/4. So if you apply this noise, it's easy to convince yourself that many clusters will merge, many others will split. And, well, there is some decorrelation that has to happen between the left and the right. But now the whole purpose of today is to prove that all the geometric information here, all the SLE6, all this rich thing that you have on the left, everything is lost once you do this noise. And somehow, this is much harder to see, and so far, the only way to understand that the whole geometric information vanishes, the only proofs that are known are the proofs that look at the frequencies here. So these three different approaches, the kind of analysis approach, the randomized algorithm, and this will be more a study of the geometry of these random sets representing the frequencies. So today we'll, so let me recall what is the spectral sample. So our Boolean function, which is our left-to-right crossing event, but this could be any Boolean function for what I'm defining now. So we'll consider that this will go into -1, 1. So this is just for convenience because by definition, this shows that the L2 norm is 1. Just the function is, its absolute value is always 1. So. And therefore, by Parseval, you get that the sum of the Fourier coefficient squared is equal to 1. So now, what you do with it is that it enables you to define a random subset of your domain. As follows. So the random subset will denote it like that. And this is the spectral sample which corresponds to the Boolean function f of n. And for any set included in our domain here, so for any subset of the bits, the probability that our spectral sample is equal to this, by definition, this will be the square of its Fourier coefficient. So somehow this whole picture can be think of as the distribution of the size of this random set. And if we understand the distribution of its size, and if we understand that almost surely this random set is this big, then we'll be done. Okay, so maybe I forgot. Maybe let me state precisely a theorem that we will prove today. So the theorem can be stated as follows. So the lim sup, or the limit only if you want, of the probability that the size of the spectral sample is small in this sense. This goes to 0 as lambda goes to 0. So the probability that you're much smaller than n to the 3/4, this goes to 0, and most of your spectral mass is indeed of order n to the 3/4. So here, this is not precise enough. In fact, I should write it like that. But to not confuse and have many notations in the rest of the talk, n to the 3/4 will mean actually these type of quantities. Okay, so the whole proof also works on Z2, so n to the 3/4 is far from being known, but this will be, n to the 3/4 will be understood as this quantity. So in fact, one can prove something more precise about how fast it goes to the n to the 3/4. And we can prove that as n goes to infinity, the probability to be less than lambda times the mean size is of order lambda to the 2/3. So there is some critical exponent here which comes from SLEs and so on. So we know exactly the behavior of the lower tail of this distribution here. So maybe at least once in this lecture I will write a precise statement that also works for Z2. The probability that the size of the spectral sample is less than lambda times its expected value this is of order lambda to the 2/3, and on Z2 you would have the corresponding quantity. So maybe this statement here is clearly a statement about the lower tail of our distribution. Okay, so somehow the idea of the proof of this theorem, so the purpose of this whole lecture won't be to give you the proof, because it would take too much time, but the purpose today is to give you the flavor of how one can prove such a theorem. So it's more about, I don't know, the flavor of the proof of this theorem. And the general idea is as follows. So somehow, to understand noise sensitivity, we only want to know what is the size of this random variable. But what we will do is we will try to analyze the law of this random subset of the bits, and we'll try to explain, to describe how it looks. So somehow if we manage to describe the geometry of how these spectral samples look, eventually we'll manage to have these kind of estimates. So we will prove quantities about the size of the spectrum through quantities about its geometry. So first question, how does it look? Well, the first thing you might wish to do is you might try to sample, to take n equals, I don't know, 1,000, And you might say, well, let's sample this random set. So there is a problem here, which is that it is very hard to sample this random set. So let me tell you the only algorithm which is known to do it, and it's pretty weak. The only algorithm is the obvious one. For any subset of the bits, you compute its Fourier coefficient. So for any S in this, so you have a lot of such sets, right? You have 2 to the n squared, roughly. You take one, and you compute its Fourier coefficient. So compute this. So what is this? Well, remind from the previous lectures that this is the expectation of Fn of omega times the product of the bits which are in omega. So already computing this single Fourier coefficient, so maybe say that the set S is something like that. So computing such a set, take this set, already computing its Fourier coefficient, it would need some time of computation, right? You would need to compute this expectation, so maybe you would sample percolation many times, I don't know, but already this is not completely trivial. And then once you have a good estimate on this, you store this value, which when S is big is extremely small, and you do this for everyone, and then you sample out of this distribution. So, well, I've done it for n equals 1 or 2, I don't know. I think 5 or 10 would already be impossible. So we don't have any picture of how it really looks. So somehow this is an issue a little bit. So just a slight simplification is from this theoretical knowledge, we know that the spectrum cannot be huge. It's never of size n. So instead of sampling and computing 2 to the n squared Fourier coefficients, we can compute only Fourier coefficients which are less than roughly n to the 3/4. So it's enough to compute more or less n squared to the n to the 3/4, because for all of these you have n squared spots, more or less. If you can do that, you're fine, but still this is an enormous number. So anyway, so it's very hard to sample the spectral sample, so we don't know exactly how it looks, but we have a guess. So So the belief is that this random frequency should look like a random self-similar Cantor set in this domain. So if n is really big, you may think just of the square. And it's believed to be a random Cantor set of Hausdorff dimension three-fourths. So this is just a belief, and we'll try to make sense of it. We won't prove it exactly, but we'll prove partially this statement, and this will be enough to conclude that its size is always large. So let me point out that a reason why such a thing was believed is that for a long time, it was believed that the spectral sample had a law very similar to the set of pivotal points. Pivotal points for or left to right crossing f of n. So this is a nice random subset of the bits. You take your domain n by n, you sample the percolation configuration, and you look at what we defined in the first lecture, which is the pivotal set, all the points that are pivotal. So let me be a little bit more precise here. There is a very easy way to sample the way this set looks. So if you take your domain n by n or n by alpha of n, you remember that an edge will be pivotal if you have a 4-arm event around this edge. So one algorithm could be you sample your omega, you sample your configuration, and for each edge, you explore around your edge, and you would check whether you have 4 arms all the way to the boundary or not. So this would be a terrible algorithm. This would take really long, but there is something much simpler and very quick. What you do is that you start an exploration process from here. So there are two cases. Either it will touch this edge, and you will have a dual crossing, or it will touch this edge. Let's say it touches this one. So this is some SLE6 curve. And now look at the exploration process starting on this corner. Now, if this exploration process goes all the way to this edge without touching this, it means you don't have any pivotal point. And this set is just empty, which happens with positive probability by a Rousseau-Semon wedge. But also with positive probability, this exploration path will bounce many times on this thing. And somehow, all the edges that you have here at the intersection, well, they are exactly your pivotal points. So in this case, it's very easy to sample it. It's somehow much easier to study it. And if this happened to be true, then we would have a way to understand this random set that we are interested in a nice way. So let me quickly enumerate some of the similarities and differences between these two sets. So okay, so so here I'll mention things about the pivotal set, and here about the spectral sample. So what we've seen in the last lecture is that they have same first moment. So what it means is that the expected number of pivotal points is exactly equal to the expected size of a random frequency. Okay, so what about the second moment? Well, also in the last lecture, Jeff proved that the second moment match. So the expected size of the pivotal set squared, this is the same as this. And somehow, now you understand why for a long time maybe people believed, well, maybe they're very similar and they look the same and so on. And this already enabled us to prove that the positive fraction of the frequencies are big just using a classical second moment method. So this was nice, but higher moments, starting at moments bigger than 3, they are different. So the similarity in terms of moments stop here. So now I say that this is easy to sample using this algorithm that I explained, and this is very hard. So it's hard to compare visually how they differ. Maybe the main difference, the two main differences are the following. In the percolation picture, here, there is a lot of independence. So in some sense, if you know that you have pivotal points lying here, and if you're told that there are some pivotal points in this box here, so this type of consideration, we'll come back to it later. But say you know you've seen the shape of the pivotal points here, and I tell you the pivotal set intersects this little box, then using coupling arguments, spatial coupling arguments and things like this, you can prove that the law of what you see inside is sort of independent of what you explored outside. Not exactly independent, but there is some decoupling. Well, in the case of the spectral sample, the dependency structure is very hard to control, and we have no idea how to deal with it, and this will be the main issue. And a slight way to rephrase it is that in the percolation picture, you have what's so-called the spatial Markov property. And somehow what this says is that once you discovered some part of the picture, for example, like that, then from the IID structure of the percolation, you know that all this part is completely IID, and you can continue working with this type of Markov property. In the case of the spectral sample, if you start exploring some region of your domain, and say you see a few of the edges which are in your spectral sample, then you don't know at all what is the conditional law of your spectral sample in the rest of the domain. Okay, so and last thing, you can make explicit computation, which I won't do, which tells you that in the large deviation regime, so at the bottom part of the spectrum, the probability that you have only one point and the probability that you have only one pivotal point, so it's another way to compare these two distributions, this will be much less likely. So maybe as an exercise, if you wanted to compute this quantity, this will do it, and we've already done it somehow before. But this quantity, what do you need to have just one pivotal point? It's not enough to have 4 arms around your pivotal point. Somehow you need this picture here to touch only once, the bottom and the above part. So what you need is a 6 arms event around your edge. And you have n squared points in your bulk, and so the quantity is something like this probability here. So this is of order that. And using the 6-arm exponent, you can see that this is very different from this quantity. So this whole thing is there to say that there are many similarities between these two things. We may use some of these, but it won't be enough to prove concentration properties about the size of the pivotal points to deduce it for the spectral sample. We need to deal with these type of issues, that there is a lack of independence, there is a lack of Markov properties, there is a lack of many things, and we need to try to deal with this. So, so let me come back to this belief here. So we're guessing, we believe that this thing looks like a self-similar Cantor set. So now what I want to do in the next 20 minutes is to get inspired from a toy model of a self-similar Cantor set, which should share many properties with our spectral sample, and try to see on a toy model how to prove that things are well concentrated. So since we believe that this should be a little bit like a random Cantor set, let's take the simplest model of a self-similar Cantor set in this domain. And the simplest one is basically Galton-Watson trees. But we wish to embed it in the same domain as our spectral sample, right, to try to compare the two things. So let us take n to be some dyadic integer. So our domain is the same as before, but with this property. And let's do a spatial Galton-Watson tree, which is well known. It's sometimes called fractal percolation, or maybe a Mandelbrot percolation also. And what you do is that at each scale, you keep your square with probability p, and you remove it with probability p. So let's take some parameter p in 0, 1. And if we want something supercritical, if we want to have many points with a positive probability, let's take this to be bigger than 1/4. So this can be thought as a, well, Galton-Watson tree over the scales. Yes, the k equals 0 scale, k equals 1. Well, until the scale k. Notations are not great, but okay. So let us call T the set that you end up with at the end. So build your Galton-Watson tree iteratively, and at the scale k, you arrive at the n by n grid. And you end up with maybe many points here, and I don't know, something like that. And let's call this random subset of your domain, let's call it T. So this random set, let's call it T. And somehow we hope that in some sense, the way it looks should be close to the way the spectral sample looks. So of course, the spectral sample won't be squarish like that, right? It will be more, but in principle, it should share some properties. So similarly as the energy spectrum that we always draw, the similar quantity here would be the following. You plug as a function of m the probability that you end up with exactly m points. Right? This is exactly what we had with your spectral sample. And if you take k to be very large, if you take many generations in your tree, the probability to be 0 is some non-trivial quantity. This is the extinction probability. But then you expect a shape to be, well, I don't know yet, but to be something fairly large because we took a supercritical Galton-Watson tree. So somehow you expect that either you lose or either the generation extinct, or it will be very large. And this is somehow what we'd like for our spectral sample. So let's just do a very simple computation. So the expectation of the size of the tree. So what is it? So at the end, you have n squared points, right? And what's the probability that one point lies in your random tree? Well, this block had to be kept with probability p, the generation after with probability p, and so on k times. So the probability for each point to be in the random set is p to the k. So this is like n squared 2 to the k log 2 of p, and 2 to the k is n. So this is n to the 2 plus log 2 of p. And let's think of it as n to the power alpha. And maybe in our analogy, we may choose alpha to be 3/4. Okay, so what we're saying is that in expectation, this distribution here lies around expectation of the tree, so around n to the alpha. Now, in the case of the tree, it's easy to compute the second moment, so you know that a positive fraction of your distribution lies here. But since it's a tree, you know much more than that. So I won't do a crash course on Galton-Watson trees, but somehow if m is the mean number of the first generation, so here it would be 4 times p, you know that the expected size of the tree at generation I divided by m to the I, this is a positive martingale. And somehow in Galton-Watson tree, there is a lot of invariance that you can play with, a lot of scale invariance, and there is a lot of independence. And somehow using these tools, you can easily prove that there is 0-1 laws, condition and non-extinction. And these 0-1 laws tells you that most of the distribution lies here. So using very classical tools, you probably already seen that you can control these quantities, and you know that either you're empty or you're very large. And today we'd like to do the same thing with the spectral sample, but somehow there is no hope to use tools like martingales because it will not behave at all like a martingale when you will go to smaller and smaller scales. So what I'll do now is I'll try to explain how to prove such an easy statement in a more complicated way, but which will be suitable for us in the case of the spectral sample. quelques minutes. So, okay, so remind that our goal is to show that if u is much smaller than n to the 3/4, then the probability that the spectral sample is less than u, we'd like to see that this is small. Okay? So that's our goal. Let's take our tree. It seems it's quite suboptimal, my way of erasing the board. I should learn from Vincent, but it's the last lecture, so it's too late. But let's take our tree. And let's take some u, which is much smaller than what you expect for the typical size of your tree. And let us understand what should be the probability that our tree did not extinct yet, but is much smaller than what you would expect. Okay? So if you want to understand this, a reasonable thing to start with is to look at the conditional law on your tree, knowing that this is anomalously small. So if you can understand this conditional law, if you can understand how your tree looks when it's conditioned to be very small, then you will know which type of configuration give weight to this probability that you are interested in. Okay? So now let us look at this conditional law. So what's important here is that we are much smaller than the typical size. And now there are two scenarios. So let's take our big box, n by n. And we're conditioning our tree to be really tiny. So well, everything is completely wet. Do you think it will look like that? Like you will have 3 tiny branches at different locations like that with some points in your tree. In each of these branches, you have less than u points, and they sum up to something less than u. Or do you think you will have one spot somewhere with less than u people? So the dichotomy here is that here you have a lot of entropy. So somehow you have a lot of choices for this type of configuration, which are more or less the volume to the cube to place your three boxes. Here you have much less entropy. You have only the volume to the 1. But if you think a little bit, it costs a lot to maintain one tiny branch alive without it to just grow like crazy. So there's a competition between this entropy term and the fact that it costs a lot to maintain at different locations tiny branches. So do you think this would happen or this with high probability? No guess? Do you prefer to put many locations, or do you prefer to focus this or that? If you don't have any guess, then for the spectral sample, we have no hope. Okay, so this is what should happen, at least in our case here. So somehow, if you believe this gives us a first understanding on what this conditional law should look like. Let's understand it slightly more. Let me rewrite this parameter u, which is much smaller than n to the 3/4. Let me rewrite it as r to the alpha. Why? This explanation said that a Galton-Watson tree on this scale n likes to be of size n to the alpha. That's its typical behavior. But now a tree is completely self-similar. So if you are in a box of size r, and if you know that the tree is alive here, then typically it will look like r to the alpha. You will have r to the alpha points here. So somehow what we're saying is that if you condition the tree to be very small, of size r to the alpha, r being much smaller than n, what it will do, the strategy it will do is it will keep just one branch or maybe two alive, but very close to each other. Because you could have the configuration of course, where you have another box here very close to it. So it will maintain basically one branch alive only. And once you reach a scale where it's comfortable enough, the scale r, then it does what it wants and it can expand to its usual behavior. So one can rephrase it as follows. So the probability, if u equals r to the alpha, the probability that we are looking for, and we used our understanding of the conditional law, we expect that this is more or less the probability that the tree is included in one R box B, and T is alive in this box. So this tiny box here will usually be called B. So of course this is not a proof yet. It's just what we're guessing. And I will introduce a notion which will be useful to rephrase that. So it's the following notion of R smoothing. So what we do here is we take, for any subset S of our domain, so typically this thing will be our spectral sample. If you take any scale R between 1 and n, and this will be a mesoscopic scale, if you take any intermediate scale like that, define smoothing of this set, S of R, to be the set of R boxes B, which intersect S. So if you want a picture, what we are doing is the following. So if I take some subset of the domain, now I want to look at this smoothing of this subset. So we take a subgrid like that. And this grid is of mesh R. And what we do is we only look at the squares like this. So somehow you take your set S, which you expect to be self-similar, and you keep some mesoscopic information about it, but you don't really care about the microscopic information inside. You just keep some macroscopic information, and that will be your what I mean by this set S of R. So to rephrase what we have here, the probability that T is less than this R to the alpha should be, if we have the right intuition, should be more or less the probability that if you take an R smoothing, if you look only at details up to scale little r, you will touch only one box. Okay? So if the analogy with the tree case was true, and we'll see that in this sense this will be true, we'll prove the following proposition. The probability that the spectral sample is small in the sense that R is much smaller than N, or let's say just smaller. We'll see that this is of the same order as the probability that if you only look at your spectral sample up to the detail little r, you will touch only one box. So of course here I didn't prove anything, but somehow our strategy will be to prove something like that. And this tells you a lot about the structure of the spectral sample. It tells you that if you consider your frequencies under this spectral measure, and if you condition it to be very small, then what it will decide to do, it will pick some box of size r, and within this box it will look like a more or less like a spectral sample there. So let me now do a small computation to see what it gives us, because is this estimate any good for us? Is this thing indeed small? So is this any good? Well, assuming we can prove this theorem, let us compute this quantity here. So what is the probability that the spectrum only seen at scale r touches only one box in this domain? Well, this is the sum over the r boxes B of the probability that the spectrum is included in this box and is non-empty. Right? So you sum over all the boxes here, and you want your spectrum to be contained in this and to be non-empty. So if you recall the lecture of Jeff, the probability that the spectral sample is included in B, by definition, this means the sum over all the frequencies that are in your set of this. This is by definition of your probability measure. So here this is f of n. And you can rewrite it like that, the expectation of the sum over S squared. Sorry, this squared. So while this, you just use the orthogonality of this chi of S. And this term, if you think of the original function, which is the sum of all the frequencies of that, if you restrict to the Fourier coefficients which are in B, this is exactly the same thing as looking at the conditional expectation of your Boolean function, knowing the bits that are in B. So if you take the conditional expectation knowing the bits in B, you only keep the frequencies that are inside B. Okay, so now we can conclude. The probability that the spectral sample is in B and is non-empty, this is the probability to be in B minus the probability to be empty. So we call that this, by definition, is the squared of this Fourier coefficient. And this Fourier coefficient was just the expectation of F. It's the projection on the constant. So one can rewrite this term from here like that. The L2 norm of the conditional expectation knowing things in the ball B minus the square of the mean. So these things, you can think of these exactly as martingales, but they are martingales in 2 dimensions somehow. And all the classical computations of martingales, they work nicely. So here you can rewrite it as the following. Basically by orthogonality. And now let us analyze what this means. It means that, so let us take our domain. Let us take the box B that we fixed here. If you want to know what this is, what this samples is only the information in B. Anything else, you forgot about it. So now, in this expectation, you know what is the percolation configuration in this box. And this minus this, you're wondering how this information helps you to cross from left to right. This information will be relevant only if outside you will get a 4-arm event. Else, you will just keep your box B, and this will be the same thing as this. So somehow, this term is always less than the probability that the box B is pivotal. And say you are in the bulk. As always, we don't really care at that point about boundary issues. This thing is of radius r. The box is of size n. So the probability that B is pivotal is less than adding 4 arms for distance little r to distance n. So this gives you a bound of alpha 4 of r to the n squared. And using the exponent, this is r over n to the power of 5 alpha. So in all this talk, I don't put the corrections and things like this. So there should be plus little o of 1, but we don't care. So altogether, what this gives us, we'll still have this entropy term here. We have many possible boxes B. So how many boxes B do we have? If you think for a second, this is of length r. You have a domain of size n. So you have n over r boxes B. Each of them contribute this. So you get this estimate. So if we manage to understand the conditional law on the spectral sample, knowing that this is small, if we manage to prove this thing, we'll get that this should be less than r over n to the power 1 half, if you believe the computation I did here. So now let us just take R to be lambda to the, so let me cheat. Well, I don't know yet which power here, times n. 4/3. So let me apply what I just explained to this mesoscopic scale R. What it gives here is exactly the probability to be less than lambda times n to the 3/4, and this is what I had in my first theorem. And what we get on the right is lambda to the 4/3 to the power 1/2, which gives lambda to the 2/3, and n over n cancels. So somehow, if this intuition that it looks a little bit like a random tree happens to be exact, then we recover the exact lower tail behavior for the spectral sample. So now, before explaining to you the strategy that will apply for the spectral sample, let me come back again for 2 minutes on the tree. I had a statement here for the tree. I didn't say how to prove such a thing. So let me explain one way to do it, which would be maybe the most horrible way to do such a thing for trees, but for spectral samples, this will be the right way to think of it. So we'll proceed as follows. I want to bound from above the probability that the tree has a size much smaller than it should have when there is no extension. And let me rewrite it as follows. Sum over k greater than 1 of the probability that the tree is small, knowing that at scale R, you touch exactly k boxes. O times the probability, and this is T, times the probability that we touch exactly k boxes. So now let us try to understand this term. So assume, so this was our domain. Assume that you know that you touch k boxes. Say you touch these k boxes. Say k equals 5. So assume you know that the tree is non-empty in all of these boxes and is empty and it doesn't touch anything else. What is very nice about Galton-Watson trees is that the behavior in each of these boxes is completely independent. Right? And furthermore, we've seen that the probability so what is this quantity? Take a box B, assume that you touch the box, so the tree remained alive until this box. Then you know that typically the tree has size R to the alpha in expectation. So from second moment method, you can prove, maybe you would need a constant here, but you can prove that with high probability, your tree is big within this box. So you can prove that this is bigger than some constant which is positive. Okay, so when you know that a tree touches a box, you know that with high probability this will be big here. So what this tells us here, we know that we touch k boxes. We know that they behave completely independently. And in each of these, there is this probability C that you're big. So this, by independence, is less than 1 minus C to the power k. Okay? So what we have is that this probability is less than the sum over k of this term which decays exponentially fast times the probability that we touch k boxes at the scale r. So now let me take k equals 3. And with the same picture as we had before, I claim that the probability that the tree will go into these 3 boxes, which are sort of far apart, is much smaller than the probability that the tiny branches are sort of localized, like this. And this is easily seen, this little group, this is easily seen to be up to constant, the same as touching just one R box. So what I'm saying here is that the probability that the tree at scale R touches only 3 boxes, even though you have all this entropy here, up to constant, this will be the same as touching just one. So now, we expect that for any k greater than 1, the probability to touch k mesoscopic boxes of size r, this should be more or less the same as touching just one. So there is some localization phenomenon going on here. But of course, if you start taking k to be very large, the entropy starts to be very important, and you start to lose more and more control on this quantity here. So the only thing that will be, so what we might hope to prove is that the probability to touch exactly k boxes will be less than some quantity which depends on k times the probability to touch only one. And if you have this, if you have such an upper bound, then this sum here will be less than the sum over the k of gk times 1 minus c to the k times the probability to touch exactly 1. So of course, I'm saying that when k is large, you lose more and more because of the entropy. You're less and less localized. But if somehow you manage to have a combinatorial proof which tells you that this is sub-exponential, if you can prove that this term is sub-exponential, then the nice thing is that this series converges, and you indeed obtain that the probability that you are of this size is of the same order as just touching one box of size R. Okay? So now, to prove this, let me tell you one statement that we prove about the spectrum. So, proposition, there exists some constant, positive, such that for any k larger than 1, and for any intermediate scale r and n, the probability that our spectral sample, but only seen up to the detail little r, so we sample the spectral sample, but we only look at the large-scale boxes that it touches, the probability that this touches exactly k boxes, this is less than some term which depend on k, and the probability to touch exactly one box. So this, we already analyzed it before. This was of order r over n to the 1/2. Now, what is the term that we managed to obtain here? How do we manage to control the entropy here? The g of k that we obtain is k to this thing. So somehow it was more and more messy when k got large, and we had this not so great estimate here, but notice that this is sub-exponential, and therefore, assuming we have a lot of independence in the spectral sample, we would be fine. So now I will assume this proposition, which is, I will give a hint on how to prove such a thing, and I'll tell you what's the rest of the proof, basically. What's the strategy of the rest of the proof. So the setup of the proof is divided as follows. A first step is to prove this thing, to prove that a localization principle for the spectral sample. So this is more or less what I explained so far. So I will say a few words about this part. The second part, which is the main part, but I won't have time to say much. Maybe I won't have time to say anything. So remember that once we had these estimates for the tree, I hope the computation is still there here. We used this estimate for controlling this term. If this was not too big, we were in good shape because here we have a lot of independence. Right? If we know that, so here we had all k boxes touched. If we know that we have exactly k boxes touched, the behavior of the tree within these boxes was completely independent. So this completely fails for the spectrum. So now we need to fight against the lack of independence to make this type of estimates work. And that's sort of the main issue. It's like finding some, proving some weak independence, or rather maybe describing the dependency structure within the spectral sample S of Fn. So this I won't have time to explain, but somehow we obtain a very weak dependency criterion, which is much weaker than that. And this makes things not so nice. So a third part is to sort of modify a little bit the setup to make the whole thing work. So it's a long program, but now I'd like to explain where this quantity comes from. So I'd like to explain why the spectral sample tends to localize. Why, when you condition the spectral sample to touch few mesoscopic boxes, why it has the tendency to just clusterize somewhere in your box. So I'll explain to you a key lemma which I think illustrates very well why things tend to localize. And for this, I need to introduce some concepts. So I'll consider, so maybe I will draw things here. So this will be our domain, the n by n domain. And I will consider a family of annuli. So, for example, this one. So there can be a nested sequence of annuli. Something like that. And another annuli may be here. So this will be, I'll call this type of structures A. A will be a family of disjoint annuli in non-domain. And now, for any set S in the domain, so for any frequency in this domain, I will say that S is compatible with the annulus structure A. So this is an annulus structure. S will be compatible with A if the two things are satisfied. We want the S to be included in the complement of the annuli. And we want, so this is the first condition, and we want S to intersect the inside of each annuli. So maybe it will be more clear on a picture. A frequency or a subset of the domain will be compatible with this annulus structure if it doesn't touch these arranged parts. It has to lie in the complement, so maybe it could have some points here. But what's very important is that in each of the inside annuli, it's non-empty. Okay? So somehow these points are not completely necessary, but they can occur if they want. These ones are not necessary. These ones are not necessary because this is also considered like the inside of this annuli, and this as well. So you have a bunch of frequencies that are compatible with a fixed annulus structure. And somehow the key lemma that I'd like to show is that the sum of all the frequencies that are compatible with A, the sum of these things, or in other words, the probability that our random spectral sample is compatible with this fixed annulus structure, we'd like to estimate what it is. And somehow you already see that if your annulus structure is like here, the probability that you have a small frequency compatible with it, you have delocalization, right? You have at different places. So the lemma says that this quantity, this probability, is bounded from above by the product over all the annulus in this annulus structure of the probability that you have 4 arms like that. So if you take an annulus A, like this, the probability that you have this, so the usual 4-arm event from the inside radius to the outside radius, I'll call it alpha 4 of this annulus. So when you take a fixed annulus structure, the probability to be compatible with it is bounded by this term. Okay, so let me explain why this indeed provides you with some localization. So if we take the case k equals 2, I'll let you imagine the mess it would be for k larger, but for k equals 2, say I want to compute the probability that my spectral sample, but only looking at the number of R boxes that it touched, say I want to look at the probability that this is 2, and that it is large. The diameter of this, say, is larger than that. So what I want to estimate is the probability that my spectrum touches only 2 mesoscopic boxes, but sort of far apart, like this. And I'd like to say that this is very unlikely. So how to estimate this? This is the sum over R boxes B1 and B2, which are distant, at least at distance n over 2, of the probability that the spectrum lies in these 2 boxes, B1 and B2. So I want some points in these 2 boxes, and I don't want any points outside of these. So now what I can do is I can use the following annulus structure. I take just 2 annuli. So this will be A1 and A2. And for once I fixed these 2 boxes, I want to know what's the probability of this. This is exactly the probability to be compatible with this annulus structure made of 2 annuli. So by my lemma, this is less than alpha 4 in the first annuli squared times alpha 4 of my second annuli squared. And now, how large is this thing? Well, I suppose that the boxes are far apart, distance n. So this is at least n over 4. I'm neglecting boundary issues again. So these terms are alpha 4 r over n squared times alpha 4 r over n squared. So using critical exponent, this thing is exactly r over n. The exponent is 5/4. You have it 4 times, so you get 5. And now, how many such boxes do you have? The number of these couple of boxes, you have r over n squared for each. So you get r over n to the power 4. Oh, yeah. Thank you. N over r to the power 4. So altogether, this gives you that this is less than r over n to the power 1. But remember that the probability that touching just 1 box, and it's easy to see that this cannot be much smaller than that. This was of order r over n to the 1/2. So having 2 boxes which are far apart is much less likely than having just 1. So now, if you want 2 boxes, you need them to be very localized together. So this key lemma, only for k equals 2, sort of explains to you why the spectrum tends to localize. So now in the last 5-10 minutes, what I'd like to do is I'd like to prove this key lemma. And why that is because if I would have done it sort of my way, it would have been very messy. It would have taken a long time. But Oded found a very clean and sort of very nice proof of it. And if you knew him, you will recognize the style. Maybe not for the presentation, but for the ideas. And I'd like to explain how he did such a lemma, the simple proof he found for this. So we take some annulus structure in the, so fix an annulus structure. Okay. And I want to look at all the frequencies which are compatible with it. So what I'll do is I will look at the following vector space. I will look at the span of all the characters which are compatible with my annulus structure. So all these things are in L2 of hypercube, and I'm just taking the linear combinations of all of these. So this set is a sublinear space of L2 of the hypercube. So just to take an example, if my annulus structure has 2 annuli, something like that, say I have a variable x1 here and variables x2, x3 here. So say I'm looking at 3 bits. The function x1 is not in my W. Why? Because the point 1 is not compatible with the annulus structure. I want points on the inside of each annuli. So this is not. So this you might think it is in the set because I have points in each. But what I want is the functions in this vector space, all their non-trivial Fourier coefficients, they have contributions coming from the inside of each annuli. So the Fourier coefficient here has a contribution only from this annuli, so this doesn't work. The product of these 2 bits, that's okay. The product of the 3 bits, that's okay also, and so on. So somehow this vector space, it's not necessarily very easy to get what it is at first sight, but its functions whose Fourier coefficients are all compatible with this. So now what we want to look at is the sum of all the Fourier coefficients which are compatible with one annulus structure A. So you may exactly write it like that. Like this, squared. And what is this thing here? Well, you can write it as the projection of your function on this linear space W, right? You only select the frequencies which are compatible with your annulus structure. So to prove the lemma, we need to estimate the L2 norm squared of the projection on this linear space here. So now if I have a the key observation is the following. Say I sample percolation in my domain, and I will call the set of bits in the annulus structure, I will call it theta. So theta will correspond to the bits which are inside the annuli. And eta will be the bits which are outside. So in what follows, a configuration of percolation, this will be decomposed as eta and, theta and eta. And this will be a percolation configuration in -1, the bits in the annulus structure. And this will be -1, the bits outside of the annulus. So now the nice thing about this projection is that you project on things which are compatible with A. So in particular, you only keep frequencies and bits which do not lie in this orange region here. You don't have any bits coming from the theta configuration. So this projection doesn't look at theta. So you can average on the value taken by on the configuration theta. So in other words, the projection of F on W, this is the same as averaging this function. So since it doesn't depend on theta, I can just average on it. So now let me define for each configuration theta, which is in this hypercube, let me define the function like this to be just the initial Boolean function, which is our left to right crossing. But I'm just fixing the function theta, and I play with the variable eta. Okay, it's just a rewriting. So what I'm saying is that the projection of our initial Boolean function f is the average of a possible configuration outside of the projection of this function. So now, what we want is the L2 norm of this L2 norm squared. Let us analyze what it is. We just said that this is the expectation of the projection of this function f of theta. And we take the norm of this. So now, using the triangular inequality, you can average outside. Triangular inequality. And this gives you that this is less than the average of the L2 norm of these projections. So now we need to notice the following. This function is built from the Boolean function here. So it has to be into -1, 1. Okay, f was in -1, 1, also f of theta. So in particular, the L2 norm of this is less than 1. Well, in fact, is 1. Now you have a projection. The projection doesn't increase the L2 norm, so the projection of your f of theta is also less than 1. So now the only thing we have to notice is that most of the time, for most values of theta, this thing is actually 0. So let's analyze why. Let me take one of the annuli in this annulus structure, let's say this one, and I sample theta, so I sample this, and now I'm wondering about this function here. Assume that I have for example, an open circuit in this annulus. So say that in the percolation configuration that I sample here, I have an open circuit here. I didn't sample yet the eta, but I see this circuit. Now you want to know about the left to right crossing. Well, it won't depend at all on the values that you have inside, right? Because you can always take the circuit outside, and the dual cannot come into this. So the f of theta, if theta has a circuit, the f of theta does not depend in a non-trivial way on any bits which are in this. In particular, the Fourier expansion of this thing won't have any Fourier coefficient with terms in this inside. And in particular, the Fourier expansion of this will have absolutely no component in this linear space W. So when you have such circuits in these things, this term is 0. And since if you have it's less than 1, this is less than the probability when you sample theta that the projection is non-trivial. And I'm saying that this probability is less than the product, over all the annulus of the probability to have. So what do you need to have to exclude this? You need to have 4 arm events as I had before. So basically, we need to have 4 arm events in each of the annuli to exclude such cancellations like that. So we get that the L2 norm of our projection is less than the product of the 4 arm events in each annuli. And initially, we had that what we wanted to compute was less than the squared of this. So we get less than the product of the whole annuli of this quantity, which proves the lemma. So as I said for k equals 2, this lemma sort of explains to you why there is a localization property for small spectral samples. And the combinatorics is quite involved, but you can generalize these ideas to k larger, and you can get this bond. And if you want to conclude, as I explained in the rest of the strategy, you need to find some notion of independence in your random subset, in your random spectral sample, and this is the main part, but I won't say anything about it. And yeah, so this sort of ends the part in this course which focuses on understanding the Fourier spectrum of Boolean functions. Tomorrow, Jeff will introduce the model of dynamical percolation in the plane, and he will prove based on all the information that we obtained so far, but he won't need to deal with the spectrum anymore. He will use all this spectral information to show that you have explosion times when you run the dynamics on critical percolation. So somehow the content of the lecture tomorrow will be completely independent of the techniques that we had so far. And in the TA session tonight by Ragnar, he will introduce the model of dynamical percolation in a simpler case on trees. And he will prove what happens in this case for trees. But still, Jeff will reintroduce the model tomorrow in his last lecture. OK, so thank you. Questions?